All right, so today we're going to talk about an extension of what we've been learning. So at the end of last semester we talked about electron configurations. We learned how electrons are organized within atoms. And now we're going to learn why that's important, okay? And it turns out that electron configurations are super important because they help us understand how and why chemical or elements bond to one another, okay? So why chemical bonding occurs and where it comes from, that's where we're going with all of this. So our objective is for everybody to be able to describe the relationship between electron configurations / electron valency and chemical bonding, okay? We're going to assess this through a lab, a project, and a quiz. And our essential questions are, why do elements bond chemically? And how does valency dictate bonding patterns? And we're going to learn a bunch of these concepts today, so I know that that word valency is new. So, here's the periodic table. And we're pretty comfortable with the periodic table at this point, right? So hydrogen's highlighted right now, and hydrogen's electron configuration is 1s1, right? That's hydrogen, okay? Now, helium's a noble gas. Helium's electron configuration is 1s2, right? The one I want to focus on right now, just to get us started, okay, is carbon. So here's carbon, the circle carbon. And the topic of today's lecture is electron configuration, valency, and bonding. Okay. So we really have to today understand what this bonding piece is all about, where it comes from, and what that has to do with this concept of valency. Okay? Valency, what in the world is that? So we're going to learn we're going to get into all of this today, and we're going to discuss more and more in depth as time goes on, okay? With any luck, we'll eventually get so interested in it that we'll want to understand things like orbitals, and that thing represents an orbital. This big sphere, it represents an orbital. What's an orbital? Well, we'll talk about that perhaps later on. But the business end of all of this is bonding, and so I just want to get to bonding right away. So here's carbon, right? And if I tell you to give me the electron configuration for carbon, you can do that, okay? So let's go all the way to carbon. Ready, set, go. 1s2, 2s2, 2p2. Good, okay? So 1s2, 2s2, 2p2. Now, if we go back in time a little bit, okay, and we remember a little bit more about carbon. Now, carbon's got an atomic number of what? Do you guys remember, or can you see on your tables, your periodic tables? What's the atomic number for carbon? 6. What's the atomic mass for carbon? What's the atomic mass? 12, right? So if carbon has an atomic number of 6, how many protons does carbon have?
6.
Good. And if it's got a mass of 12, how many neutrons does it have? 6. Good, good. Nobody said 12. Smart, right? So let's go ahead and just draw this for carbon. 1, 2, 3, 4, 5, 6 protons. 1, 2, 3, 4, 5, 6 neutrons. And then we already count, right? Let's go. Let's count though. Ready, set, 2, 4, 6 electrons, okay? And remember, how many electrons go in the first shell?
2.
2. Okay. 2 electrons. And oh scholars, my scholars, look here. 1s, how many? 2. First shell, how many electrons? 2. Now, second shell can hold up to how many?
8.
Good. But how many does carbon have?
2. 4.
4 electrons in that second shell. So we go 1, 2, 3, 4 in that second shell. And there we have it, right? And so it turns out that chemical properties for almost any element stem from the number of outer shell electrons that that element has. So how many outer shell electrons does carbon have?
6.
Let's look. Outer shell, outer shell, outer shell. 4, right? And we can get that outer shell number in one of two ways. We can draw the diagram and actually conceptualize those electrons in the outer shell, or we can just look right here and we can say, oh, 2 plus 2 gives us 4, right? So we got to look at that outer shell. And that outer shell ends up being the really important part. Okay? Outer shell really matters. I'm going to erase this drawing and leave carbon up there.
Can I ask you a question?
You can do this, right? You don't need my help to do this, right? Right? We all took our quiz. Terrell, go ahead.
So like, how would you know to add the electrons if one says 2s2 and the other says 2p2, and they got different they're in different what's it called sections? Because that's p and that's s.
Good. Okay. So it turns out that this is called the second shell or the second principal energy level, and that consists of subshells or orbitals with designations s and p. Okay. So for you right now, you want to say to yourself, second shell, these are my two subshells, but they're still within the second shell, so there are 4 electrons in the second shell as a whole.
So it's based off the 2, like the...
Yeah, it's based off the 2, that's right, Terrell. Yep, good. Okay, so here's what we need to know. Draw a better looking A there. So valence electrons are outer shell electrons. Okay, and I'll put a little dot there. So valence electrons are outer shell electrons. Atoms tend to accept donate or share electrons to achieve the same valency as their nearest noble gas. Okay? And remember, noble gases are inert. They don't bond. So there's something super special about the noble gases and their electron configurations. The noble gases have full outer shells. They don't bond. Neon, 1s2, 2s2, 2p6. 2p6, it's full, okay? It's got a full outer shell. It doesn't bond. The noble gases do not bond, right? They don't do it. All the other elements do. The noble gases don't. Argon, okay, 1s2, 2s2, 2p6, 3s2, 3p6, right? Full outer shell, does not bond, right? Doesn't do it, okay? What's going on, right? So it just turns out that when elements have full outer shells, okay, when they're among the noble gases, they don't bond. Everything else bonds. Noble gases don't. All the other elements are trying to achieve that nobility. They want to be that stable. They have to find another way to do it. They have to work with each other. They weren't born with this like noble character, right? They weren't born stable like the noble gases were, okay? The other elements were born into a different life, and they have to go through a very different existence of combining with other elements to achieve that same stable valency, okay? So we're going to keep talking about carbon. May I erase these 2 little bullet points here? Okay, good. I see a lot of head nodding. Perfect. I'll erase. All right, so here's the deal with carbon. And we're going to go somewhere pretty cool with this, and there's a reason I chose carbon. So stick with me, guys. Probably probably another 5 minutes of lecture, but then we're moving on, and I promise it's worth it, okay? Today's lecture is worth it. You've been busting your chops to learn about electron configurations on faith. You trusted me and you said, hey, electron configurations, Dr. J says we gotta know, Today's the day you get to know why, okay? Today's the day you get to understand why this stuff is so important. So, carbon, right? And it starts here, carbon. I chose carbon for a reason. Carbon is the most important element for life, okay? Life on planet Earth. Without carbon, there's no life, okay? You need a bunch of other elements too. It's not like there are other elements that aren't required. The carbon's the amazing, unique one that is required for all life on Earth, okay? And it allows nature to construct all of these amazing chemicals that allow us to be who we are and exist as we do, okay? And we're going to get into that, especially later on, because we're going to be studying something very fun, starts with an F, rhymes with rude, okay? And it's made of all kinds of carbon compounds, right? Okay, so here's the deal. Shh, listen up. So carbon's got how many valence electrons?
4.
4, okay? 4 outer shell electrons, 4 valence electrons. So how many more electrons does it need to become like neon? It needs 4 more. Okay, so look. Carbon needs 4 additional electrons to become like neon. So here's the cool part. Because of this, carbon makes 4 bonds. Exactly 4 bonds. It never changes that up, okay? The number of electrons that this guy needs to get over to neon, that's the number of bonds that it makes. Alright? So, get that really comfortable, right? Get really comfortable with that concept, because it's really important. And now we're going to go a little fast, okay? Because I want to get to the punchline, because you deserve that punchline. Next one we're going to look at is oxygen, okay? Oxygen's right here. Oxygen has electron configuration. Ready? Let's do this, okay? We're going to oxygen on the count of 3. 1, 2, 3. 1s2. 2s2. 2p4. How many outer shell electrons, scholars? 2 plus 4 gives? 6, right? We're only worried about the second shell. 2 plus 4, 6 outer shell electrons. How many more electrons does oxygen need to become like neon? 2. Okay, so oxygen, okay, 2 electrons from neon. Okay, so oxygen makes how many bonds? It's 2 electrons from neon, so how many bonds is it going to make? 2 bonds. Okay, it makes 2 bonds. Makes 2 bonds. Alright, last one. We already did this earlier. Hydrogen. Electron configuration for hydrogen is? On the count of 3. 1, 2, 3. 1s1. 1s1. Right? So hydrogen's 1s1. Okay? How many outer shell electrons does hydrogen have? 1. Right? Very good. Okay? And then how many electrons does it need to gain to become like helium? 1. Okay? So hydrogen, right? This guy has 1 valence electron, and it needs 1 more to be like helium. Okay, so how many bonds is hydrogen going to make, scholars?
1.
Hydrogen needs 1 electron to be like helium, so it's going to make 1 bond. Okay, so hydrogen makes 1 bond. Okay, now this is the point in the proceedings when hydrogen and oxygen are going to steal the show. Carbon's been leading the way, and carbon will come back to, because carbon matters. But hydrogen and oxygen have to have their moment too. They have to have their moment for life, right? Because we wouldn't be able to live without oxygen. We wouldn't be able to live without hydrogen. And here's the cool thing. We can represent, and we'll do more and more of this later, so don't worry if this seems foreign right now. But we can represent these outer shell electrons with dots. I'm going to put 2 of these dots on top and 2 of them on the bottom for oxygen. I'm going to put 1 here and 1 here. Notice we said oxygen has 1, 2, 3, 4, 5, 6 valence electrons. 2 plus 4 gives 6. So look, 1, 2, 3, 4, 5, 6 dots for oxygen. Okay? And the ordering will make sense after a little bit. Here's hydrogen. Hydrogen gets 1 dot. Oh look, I'm going to draw another hydrogen. It gets another dot. We can bring these guys together. This hydrogen can come on over here. This hydrogen can come on over here. So here's another way to draw these guys all put together. 3, 4, 5, 6, 7, 8. Here's my hydrogen. Here's my hydrogen. Now, how many valence electrons does helium have? 1 has 2, so helium has 2 valence electrons. Now look, this hydrogen has access here to how many electrons? 2. He's